Yeah, okay. So we'll continue with the solid state, and the topic is interstitial voids. Interstitial voids. We have hexagonal closed packing, where you could see we have 6 spheres combining. I've shown you already. So what happens in a hexagonal closed packing, also as well as in cubic closed packing, only 74% of the available space in the lattice is actually occupied by the spheres. When I say the spheres, they are the atoms which are present at the lattice points. So the remaining space obviously is vacant. So the remaining space here is vacant. And that vacant space only is constituting to interstitial voids, or you can just call them holes, or you can call them interstices. Okay, these are spaces now. So whenever you see there's a triangular void, that is the space, we have different spaces. So in that we have 2 types of voids. One is the tetrahedral void. Next is the octahedral void. We will learn about these two in detail. So look at the tetrahedral void. What happens in a tetrahedral void is in the closed packing arrangement. So when you have a closed packing arrangement, you know, right? We have one layer ABC type, AB type, all these now. So in closed packing arrangement, each sphere in the second layer, okay, each sphere, please, while writing, read it also. Each sphere in the second layer, what happens? It actually rests on the hollow space. I showed you now there was a triangular space. That is a triangular void. So it rests on that hollow sphere, like space, in the 3 touching spheres of first layer. So you anyways know this, I can show you also. So if you have a so see, look at this triangle array. So whatever I'm drawing, so you have triangles here, triangle. You have a triangle. In that space only on the second layer, you're putting 1. Right? So in the closed packing arrangement, each sphere in the second layer, it actually rests on the hollow space between where you can see there are 3 spheres touching each other. In between spaces only there is the second layer being present, right? And the center of these 4 spheres are at the corner. Okay, I can write down this. Just let me know once you're done with this. We'll continue with the tetrahedral void. Can I clear the screen? Can I get a yes from everyone? If you have copied it in the chat box.
Yeah.
I got a yes from Adhyasha alone. Quickly, others also tell. I'll clear the screen and we'll continue with the tetrahedral voids. Good. So in the tetrahedral voids, I showed you now. So what happened? Let me write. So now the centers of these four spheres, I'll draw them for you, are at the corners of a regular tetrahedron. So whatever vacant space that is present between these four spheres, between the four touching spheres, is only the tetrahedral void. I'll draw it and show. See, I have a circle. I have a circle. I also have a circle. Okay. On top of this, you put a other one. Okay. If you now look at this center, you have one. Let me arrange. So what happens here is, if you have a circle, you have a circle here, behind it, a circle here. Then the center here, center of the circle, center of the circle, center of the circle. If you combine them, you have a tetrahedron. So the space in between is actually in shape of a tetrahedron. That's why we are saying it's a tetrahedral void. So in a closed packing, closed packing, the number of tetrahedral voids is very important. The number of tetrahedral voids is equals to double the number of spheres. Double the number of spheres. So there are 2 tetrahedral voids for each sphere. What did they say? Voids, number of tetrahedral voids is equal to double the number of spheres. So there are 2 tetrahedral voids for every sphere. Keep this in mind. Okay. Next information about it is the radius of the tetrahedral void. The radius of the tetrahedral void, which is relative to the radius of sphere, is actually 0.225. You have to remember it. That is what? The radius of the void to the radius of the sphere is only 0.225. This much is only about tetrahedral voids. Next, we are going to write about the octahedral voids. This is the continuation for the tetrahedral voids. So let me know if I can clear the screen after you're done copying. Can you tell me if you're done?
Done.
Good. So next we actually have octahedral voids. Octahedral voids. So we just understood what a tetrahedral. So in the octahedral, what happens is when you generally have three spheres like this, you're going to put three more on top of this. How? You have 1, 2, and 3. So it's like this, 3 on 3. So octahedral voids means here the spheres in the second layer, they rest on the triangular voids in the first layer. However, one half of the triangular void in the first layer are occupied by the spheres in the second layer, while the other half are actually remained unoccupied. So what happens? Whatever triangular voids are there in the first layer, they're actually overlapped by the triangular voids in the second layer. So this interstitial voids, which is formed by combination of two triangular voids of the first and the second layer, this is called octahedral void, because here it is enclosed between 6 spheres, first layer and then second layer. So I'll have to write all of it maybe. So the octahedral voids, as I said. So first what happens now? The spheres in second layer, spheres in the second layer, they rest on the triangular voids, the triangular voids in the first layer. The triangular voids in the first layer. However, one half of the triangular voids, okay, are occupied by spheres of second layer. While other half remains unoccupied. The triangular voids in the first sphere, are overlapped by the triangular voids, correct? No, triangular voids of second layer in this case. So the void formed by combination of the two triangular voids of the first interstitial the void formed by the combination of two triangular voids of the first and the second layer. First and second layer is the octahedral void. Why? Because 6 spheres, the center of which occupy corners of regular octahedron. The 6 spheres have centers, all of them when you combine, you have an octahedron form. This is about the octahedron void. I'll draw again. Once you're done with this, we'll write the radius. I will draw it. Can I clear? Okay. When you have so there's some overlap here. If you observe center of this, center of this, center of this, this, everywhere if you combine, you're getting a triangle like this and a triangle like this. So it's like you have a triangle like this and a triangle like this. So it's a octahedron that is formed. Also, in closed packing, the number of octahedral voids is equal to the number of spheres. There it was double, na? So for there is only one octahedral void associated with each sphere or each atom or whatever we consider. So the radius of octahedral void, here as I say, it is R void by R sphere is equals to 0.414. So yeah, this is about the octahedral tetrahedral voids, but let me tell you how do you locate them. So if you're done copying this small part, I can go forward and we will see how do we locate the tetrahedral and octahedral voids. So I'm clearing it as you're done. So next, what is it? I said, how do we locate the tetrahedral or octahedral voids? How do we locate? So what happens is, when you have a closed packed structure, in closed packed structure, that is CCP or HCP, if there are n spheres, means what? Either atoms or ions, whatever. Okay, they are in the packing, some packing. Then I said that number of octahedral voids would be n only, whereas number of tetrahedral would be what? 2n. Okay, so what happens? If at all, if example, if a closed cubic packing structure, not if, in example, no, in a closed cubic packing structure, there is one octahedral void. There is one octahedral void in the center of the body. Okay, in the center of the body, and there are 12 octahedral voids. How many spheres are there? Those many, no. On the edges. Each one of which is common to 4 unit cells. You know, 1 unit cell is 1 cube. So, what will happen? We have to see the effective number of octahedral voids. Will be what? Because 12 are there, each one is contributing to 4. You have 3. Okay. Also, you have one octahedral in the body at the center. That is 1. So you have 3 plus 1, 4 voids. There are 4 octahedral voids. If at all there is 4 octahedral voids, you obviously know there are 8 tetrahedral voids. There are 8 tetrahedral voids and 4 octahedral voids according to the example that I have given. Let me know if I can clear. Okay. Clearing it. So next you have, by then you understood after calculating the number of octahedral voids, if you're multiplying it with 2, you would get the number of tetrahedral. As it is equal to the number of spheres. Once you know the number of spheres, it's easy to answer both the number of octahedral and the tetrahedral voids which are present. Okay. So we're done with the interstitial voids. Let us look at the size. We have seen the radius of them, right? 0.414 and 0.255. Let us also derive the size of them. So in the, just now we have I have given you the radius, right, for the octahedral 0.414 and for the tetrahedral. We are right now just deriving them. This is there for your this will be there for your theoretical exams like the subjective exams and also your competitive exams surely. So we're now trying to derive the relationship between, this is the derivation of the relationship between radius of the octahedral void, and the radius of the atom in closed packing. So let me show you this circle here, a circle here, a circle here, a circle here, and if you put a circle here, this is the 4 centers. From here I have a triangle A, B, C. You can see this is the R, capital R, which is the radius of the sphere. This capital R is the radius of the sphere. This capital R also is the radius of the sphere. This capital R is also the radius of the sphere. Next you have, if you want the radius of the sphere, you have R and R, because that is the void now, octahedral void. So what happens here? You know that ABC is right-angled triangle. Right-angled triangle. Okay, this A. Center of void is A. So if you apply the Pythagoras theorem, you have a triangle anyways. So your BC square is equals to AB square plus AC square. Your BC, if you look at it, it is 2R, is equals to R plus R square, which obviously can be written as 2 into R plus R square, which will also be 4R square by 2, or it just can be R plus R square. So from here, what will you get from here? You have root 2 is equals to R plus R whole square. Root 2R is equals to R plus R. So R is equals to root 2R minus R. Root 2R means what? 1.414. 1.414 minus 1R. So your R is equals to 0.414R. Let me know once you're done. You can also try all by yourself from after you copy also once. So I'm clearing it. You're done, right? Is there anyone who's still copying? So exactly the same we are going to do for the tetrahedral void. So for that, what you have to do, you have a A, B, C, and D. This is A. So what happened here? Let us take the length of side of cube B. So from the triangle, from right angled triangle ABC, face diagonal will be AB is equals to root over AC square plus BC square, which is root over A square plus A square is equals to root 2A. As spheres A and B are actually touching each other. In the diagram, we actually draw in a smaller size. As both of them are actually touching each other. Your face diagonal AB is equals to 2R. So 2R is equals to root 2A. That is what we got, AB. So R is equals to A by root 2. So again, when you have your AD is equals to root over the second one, AB square plus BD square, you have root over root 2A square plus A square, which is root 3A. 1 second. Sorry. Yeah, so we have root 3A. Yeah, I don't have space. Please let me know if you're done. We'll continue. Can I clear? I think you all are now remembering the class, like maths. Maybe you have a lot of derivations. Now you're also learning it here. So maybe I have some space here. I don't know. After root 3a, what happened? So after this, you know that obviously the size of a void would be quite smaller compared to the actual sphere, right? So, but as the void touches the other spheres, your body diagonal, the body diagonal AD will not be only 2r, we'll have 2 into the capital R plus small r. The small r is nothing but the radius of the void. So 2r plus r will be root 3a, and r plus r is equals to root 3 by 2a. This is equation 2 and this is equation 1. I have to solve both of them. Let me know if you're all done copying this part. I'll continue with solving with the equation 1 and 2, which will give you the radius, which is 0.225. So you run as you say. So after that we have two equations, right? So let us divide the equation 2 by 1. Then I'll have capital R plus small r by capital R, root 3 by 2a, divide by a by root 2 is equals to root 3 by root 2. So 1 plus, if you take capital R common, is equals to root 3 by root 2, which is 1.225. Obviously, R by capital R is equals to 1.225 minus 1, which is 0.225. So R is nothing but relatively we are taking one. So R is nothing but 0.225 times the R. That's what is the previous one also. What is it? R is nothing but previous one was 0.414 R for the octahedral. For tetrahedral, this is it. I think in like 30 seconds, I'll clear this. I'll just draw a small table which helps you, which helps in JEE questions and also NEET question answers to directly answer if you remember the table. See the derivation, don't worry so much. You can just remember. But in the exam, they won't ask you anything other than the final answer. You'll have to only use the comparison, the relative comparison. No need to worry. But for JEE, I think, you need to be very clear with concepts, or like from where are we arriving with the values, whichever we are using for JEE advanced specifically. Can I clear the screen then? I think you might have all completed for sure. So you can see the radius ratio of R plus and R minus is cation and anion. We are specifically writing the radius ratio for in 1:1 or AB type structure. I'll tell you what you'll understand. Okay. Structural arrangement. Coordination number. And the examples that are there. So the ratio R by R is one. (0.225 to 0.414. The arrangement is tetrahedral. Coordination number is 4. Example is CuCl, CuBr, CuI, BAS, HGS. If it is 0.414 to 0.732, it is octahedral. If you get the values while calculation, it's MgO, NaBr, calcium sulfide, manganese oxide, potassium bromide, calcium oxide. 0.732 to 1, it is cubic, 8, cesium chloride, cesium bromide, NH4Br, TLBr. This is a good table. This is specifically for AB type structure. And next we are we will deal with all these in specific, the CSCL structure, how each of them are there and all of it. So please let me know once you're done. Okay, so we will continue with the ionic crystals in the coming class in detail. We are going to study about some of the important crystals in detail. Maybe in 2 or 3 more classes, the teaching part of solid state will be completely over. Then slowly we can solve a good number of questions. Okay, thank you all. Good night. I'll see you in the next class. Thank you. Assuming all of you have copied and cleared in the screen. Thank you.